So this will be, as he said, the second part of the talk, but I will assume very minimally from the first talk, hardly anything. I will review whatever I need, and just that certain connections will be better for people who attended the first talk. Okay, but I hope that still everything should be followable by people. Two things. First is I again do not see the chat, or I don't see the people. So in case you have any questions, please interrupt and ask. That is very good. Or if someone posts it on chat, I would request Saikat or Sri Hari or Ananta Krishna to interrupt and ask me the question. Okay. So let us begin. The last part of the talk will be some new results with my two co-authors, Omer Bobrowski in Technion and Matthias Schulte in Hamburg, Germany. And this paper is already on archive. You can find it from my website as well. Okay. Let's anyway get to the talk. Okay, so the first talk, let me briefly recollect the key points, is that we have a data which is a bunch of points in the torus. Okay, IID points, these are IID and random in number. Okay, the random number for me is a Poisson random variable. Okay, this is RV stands for random variable. So I have a Poisson number. This is the mean of the Poisson random variable. Okay. So this is a Poisson random variable with mean n. And so I have a random number of IID random points in the torus. I look at the Boolean model. Okay. The Boolean model is union of R balls in the torus. Okay. The R balls are in the toroidal metric. So I have this union of R balls. The reason for studying the Boolean model was is not important for us in this talk, but this was motivated by some questions in topological data analysis to understand the topology of the torus, okay, as the simplest setting. Next thing, what we introduced towards the end of the talk was a distance function, dn. dn of x for every point x is the toroidal distance to the closest data point. I look at all the data points, there are nn of them. And I look, this is the toroidal metric. Okay, I look at the closest point. So this is the distance. Okay, and now the important thing connecting the Boolean model and the distance function. Okay, this is again, we will recollect it again, but distance function. Okay, is this thing that the sub-level set of the distance function is nothing but the Boolean model. Okay, Boolean model at parameter r is nothing but the sub-level set of the distance function. This is a very easy, just a straightforward relation between the ball. Each ball is nothing but this, and this exactly this relation. Okay, and the key thing in last lecture of importance to us is that Morse theory tells you critical levels are connected to the changes in topology of the Boolean model. As R varies, the topology of the Boolean model changes, and at which level does it change is dependent on the critical level R. Whenever R is the critical level, this changes. Okay, so this was what we tried to explain last time. I will go over this briefly, but this talk will be focused completely on critical levels. This talk is going to be about critical levels, critical points, everything about that corresponding to the distance function. Okay, but this is an important motivation to know that this is connected to the topology. And one thing we saw last time, but not so much important for us this time, is that there was a threshold for connectivity, which is much smaller than the threshold for coverage. That is, what is the R at which this covers the torus? What is the R at which this is connected? The Boolean model is connected for some R. It covers the entire torus for some R. And this just means that the latter R is much larger than the other connectivity one. Okay, the R you need for coverage is much larger than the R for connectivity. Okay, so well, more precisely 2 times, but that is significant in this business still. Okay, let us just briefly run over the main point of Morse theory. What is the main point of Morse theory? This is a height function. Okay, look at the height function of the torus. So this is for me 1, 2. So this is height 1. This is height, I would say 2. This is 3. And this is slightly different to last time, but it doesn't matter. 4 and 5. Okay. So this is the height function. And now all you look at is TR is F is this. This is F for me. Okay. Is F less than equal to R? Okay. So this is T1. Let's say this is T1. Okay. Up to height 1, I don't see anything. I see only a cap. There is nothing. At T2, you see a change. You see a loop here. At T2, you see this loop. Okay, the topology changes. You get a hole. Okay, and T3, you don't actually change in topology. That's important. Okay, this is T4, and let's say this is T4 and a half. Okay, so there is no topological change. These two are homotopically equivalent. These two are not. Then there is a change again here. Okay, there is some change at T4. At height 4, I pass through this point. Okay. You get to this loop, extra loop now, because you are here. You find a new loop. Okay. So this is happening at T4 because of this point. And now there is no change again here. Okay. And if you compare, if you look at the full torus, there is a change actually, should be mentioned, T5. T5 is the torus itself. Okay, the full torus itself you see. Okay, so this is the height function on the torus. You have a function which measures the height of the torus when it is put vertically. Okay, you put the torus vertically and you look at the height function. Okay, you look at the part of the torus whose height is less than equal to R, and it changes precisely at 4 places. First is at 0, of course, and then second is at 2. Then the third change is at 4, and then at 5. Okay, exactly the changes. T0 is here. So T0 is empty set. Okay, so it changes at 0. Oh, sorry, T0 is equal to this. It is a single point. This is contractible to a single point. T0 is equivalent to T1. This is a cap which is contractible to a single point. Okay. So at 0 you have a change, then at 2, then at 4, and then at 5. Okay. So these are the changes. Okay. So this is all nice. And Morse theory essentially tells you this. The changes occur exactly at these particular levels, which are called the critical level. For us, the critical level here is, I'll maybe circle the critical levels. It is 2, 0, 4, and 5. Okay, these are the critical levels. Okay, now let's define these things more formally. How can we define it more formally? Just very quickly, this is something we did already last time. I'll go over it quickly. Suppose you have a nice function, second derivatives exist and all that. Sublevel sets are the sets which are below R. Okay, the part of the torus which lies within R. And then the critical points are those points at which the gradient vanishes. Okay, very simple. Critical levels are the values of the critical points. Okay, you look at all the critical points, look at their values. These are the critical levels, and the topology changes at these. Further, you can classify the critical levels as per some index from 0 to D. How do you do this? Very simple. You look at the Hessian matrix, the second matrix of second derivatives. Okay. The number of negative eigenvalues of the Hessian gives you the k critical points. Okay. So this is one, the main way to classify critical points. This is important for us. I'm not going to tell you how this helps. Okay. it is important that you get more information by knowing whether a critical point is of which level. We discussed this briefly last time. And what is the importance of Morse theory? Like I said, this is global. Okay, change in topology is very global information, and this is local. So you know a change occurs very locally, but to know what type of change occurs will actually not be local. That is global. The kind of change that occurs is global, but change occurs is local. So Morse theory is useful in the sense that it tells you a change occurs. Why is it local? Because it involves just gradients and Hessian. These are all local information. You need to know only f in a neighborhood of a point to understand it. Okay. So to know a point is critical, you need to know only locally around the point. Okay. So what about data? Let's go back to our question. What is the use of Morse theory if I have a data set, a bunch of random points, IID? Does it help me? Well, I've already given the clue. Is that distance function? Okay, we have a distance function. We can use this. Okay, but there is a problem, right? What about gradient, Hessian, and all that for distance function? This is not smooth. Okay, this is not a differentiable function, nice differentiable function. There is a problem. But okay, this is exactly what we discussed before. Point, I'm not going to do it in detail, but dn is not a smooth function, but it can be approximated very well by smooth functions. So because it's a minimum of smooth functions, okay, this is a minimum of nice functions. Each of this is a nice function. So dt is nice. And this is a minimum of nice functions. Okay, so that is why you can carry over Morse theory. So critical levels of dn will tell you changes in topology of this. Okay, and the rest of the talk will be only about this. We will now precisely define a critical point, everything. So this is just a outset, just a warm up for the talk. I'm recollecting briefly what I did before, but going forwards, even if you don't understand this connection, the talk is purely, I would think, well, if you just believe that understanding critical levels is interesting enough, the rest of the talk is still interesting. Okay. Okay, and there will be parts to the talk. Some part will be purely about critical levels and sharp threshold. Then there will be a part on some convergence, and the last part will be proof, will be somewhat very, a very generic idea that can be used in various probability situations. Okay, so there will be, I would say, at least two different parts to the talk, which somewhat can be followed independently. Okay, so let's get to critical levels. Define a critical level. So definition, let's get into it more seriously. So I will define critical level of index k itself directly, critical point and critical level. So this is a subset of torus times r plus. So Ci are critical points. Okay, Ci, this belongs to the torus. Ri, this belongs to r plus. Okay, so these are a bunch of points. I'm saying there are a bunch of points called critical points and critical levels, which in some way are defined. Critical points are where the gradient vanishes, and Ri is the corresponding value. F of Ci is Ri. So I should have pointed it out here. Ri is nothing but dn of Ci. So Ri is nothing but dn of Ci. Okay, so this is exactly what we said before. Okay, as I said, dn is not smooth and all that, but it can be approximated. But okay, whenever you're approximating something by something, there is one question. Does the definition of critical point of dn depend on the approximation? Ideally not. You want it to be independent of the approximation. So here is the definition. So a critical point and a level C, R, a pair is generated in MK. Remember, if I know C, I know R. If you tell me C, if you tell me C, I tell you R, okay? But anyway, C comma R is a pair, okay? Is in MK, this is an index K, okay? Is generated by a K plus 1 tuple of data points. Okay, I should have used capital everywhere. Excuse the typo. Okay, all should be capital. Okay, so a K plus 1 tuple, let me not put capital, it's making it messier. So a K plus 1 tuple of data points generates a critical pair if two things. If the point lies on the boundary of a ball of radius r at C. Okay, this is boundary of BR of C. That is, I take a ball of radius r centered at C, and all these points should lie on the boundary, and C should be in the convex hull of those K plus 1 points. Okay, both are important. First condition is this. What about second condition? Is that there should be, I will quickly show the figures, is that there should be no other point of the point process in the open ball. This is interior. Okay, BR is a closed ball. This is the interior. Okay, so there should be no other data point within the interior. So that is a critical. Okay, that is a critical point. C is such that it's a pair. C comes with C comma R. Okay, so C comma R belongs to MK. If I take a ball of radius R at C, I should find K plus 1 points of data, K plus 1 data points on the boundary. The center should be in the convex hull, and there should be no other data point in the interior. Okay, so this is what it is. Let's look at two examples. Very simple examples. Okay, first case, this is my x0 and this is x1, and well, I copied the figure from Omer Bobrowski's paper. He uses rho 1 instead of r1. So rho 1 is equal to r1, and what do we have here is c1 comma r1 belongs to m1. That is, they are a critical point of index 1. Okay, index 1 critical point. This is index 1. As you see, there are only 2 points, and both of them lie on the ball, x0 and x1. Okay, and there is no other point within the ball. And C1 is, of course, in the convex hull. It's a midpoint, okay, between the 2 points. So it's in the convex hull. Okay, that is important. Now let's look at the next case of index 2 critical points. What is happening here? I take it x0, x1, x2. Okay, C2 is this. Rho 2 for me is equal to R2. So I take C2 comma R2 belongs to M2. Okay, because a ball of radius R2 at C2 contains exactly 3 points on the boundary and nothing inside. Exactly 3 on the boundary and nothing inside. And C2 is in the convex hull generated by these 3 points. Okay, so convex hull generated by these 3 points will always be a simplex. Okay, will be a simplex, and it's in the inside that. Okay, that's the point. Okay, so this is the key, this thing. Okay, so let's understand this a bit more in detail. Let's come back to the first example. Let's see what's happening. Okay, this is x0, this is x1. Okay, rho 1 is r1, forget that, index 1. C1 comma rho 1 belongs to M1. Why is the topology changing? Suppose x0 and x1, there exists no path. Okay, no path. of, I connect any 2 points which are within distance r. Say no path between x0 and x1 in C eta n r minus. That is, I look strictly less than r. I look at the union of balls. Okay, I put union of balls here. All strictly less than r. Suppose there is no path here. Okay, then what would happen when I put this ball? So r1 minus, sorry, r1 is equal to rho 1. So just before r1, just before the ball b1 is put at c1, right? What's happening? Just before I put a ball of radius r1 at so we know this b r1 of x0 intersects b r1 of x1 is non-empty. Okay, they both get connected at r1. When you put balls of radius r1, x0 and x1 are connected. But if there is no path, then this is the first time they are getting connected. So the number of components is changing. The number of components in C eta n r minus is changing. But if there is a path already, what happens is you are creating a cycle. Okay, by putting this ball. So if implies B0 changes, which is number of components. B0 was number of components. If there exists a path already, B1 changes. Okay, this is the point that's happening. That by putting this two balls, by putting the edge or connecting these 2 points at R1, either you are creating a path between the 2 points or you are creating a cycle. So which means either B0 is changing or B1 is changing. Okay, that is all. This is exactly what's happening. Okay. Okay, so that is good. And let me say similarly here, this will imply either, so B0, B1 are Betty 0 and Betty 1. Bi is Betty 1. Okay, similarly here, so either B1 increases, and as you can see, what's happening is very specific, or B2 increases. Here B0 will decrease, the number of connected components will decrease, the number of cycles can increase. Okay, so this is what can happen. At this critical point, either you get a new cycle or you destroy a component. Okay, but this is the topological thing. Again, as I say, it's good to know this, but you can even forget it and take Morse critical points as a interesting object by themselves. We can still move on with the talk. Okay, you should be able to follow. So this is a definition. Let me flash it again so that everything is going to be based on this. If there are any questions, please. I'll just give a minute to answer anything. Okay, fine. So let's go back to our question. Okay, what do we have? What do we have? We have a data, okay, bunch of points, and then which are random in number, IID points. We have the distance function, well approximated by smooth functions. We can make sense of critical points and critical levels. Okay, Ci is a critical point, Ri is a critical level, as pointed out already. dn of Ci is equal to Ri. Ci belongs to the torus. Again, it's worth emphasizing, Ri belongs to the positive half of the real line. Now, like a lot of things in probability, it is quite about the scale. The scale at which you are looking at is very important. Okay, so Mk0 is the number of critical points such that the critical level is greater than this factor. Let's parse this factor. Theta d is volume of unit ball in d dimension. A naught belongs to R. It is some real number. Okay, I don't need to take necessarily non-negative here because, you know, as n becomes infinity, as n goes to infinity, you know, this is going off to infinity. So A naught can be any real number. Still, this will be positive. Okay, so I don't need to worry. A naught belongs to R. So I look at the number of critical points whose level is greater than this. We will come. Why are we going to look at this particular thing? Okay, look at this is A naught. Okay, log n plus k minus 1 depends on k as well. Log n. So the first term does not depend on k. The denominator does not depend on k. K is only dependent here. Okay. And I call this as mk0, the total number of such points, because of a0 and 0 is to just denote I'm truncating, I'm looking only above a0. Okay. And to the power 1 over d, the dimension is here. Okay. And a very nice result proved by Omer Bobrowski and Shmuel Weinberger, and later by Bobrowski extended also further, is the following. That everything is now explained. Why did we do this? Because the expectation and the variance converge to a constant. They converge to a constant explicit in terms of A naught. dk is a constant depending on theta d, d dimension, unit ball, some Jacobian, and all kind of geometric things are hidden in dk. Okay, there are various geometric things hidden in dk. So dk is in some sense geometric. Okay. Okay. So that is dk. So why is this interesting? Let's make sense of this result. Again, I've just restated the result for convenience. Okay. There is a consequence. What we discussed last time hinted what we want to do, and this is the proof, is once you have, actually the hard part is in this. Okay, I'm of course in a talk I'm going to tell you only the easy parts, and the hard parts are somewhat suppressed. Okay, so what is hidden is that you compute this expectation and variance, and then there are two classical probability bounds. Okay, what are the two bounds? This is called Markov's inequality. Okay, and this is called the second moment bound. It's a lower bound. So you have an upper and lower bound if x is a integer valued random variable, 0 also allowed, non-negative integer. Okay, if x is a non-negative integer valued random variable, then I can upper and lower bound probability of x being greater than or equal to 1. Okay, and let's parse it. What we said last time, we made precise sense. I will restate this again. First is a quick statement that there is a threshold or transition for k critical points at this level. At n theta Rn d equal to log n plus k minus 1 log n. What does it mean? If I look at critical points above level Rn satisfying this condition, there is nothing. Okay. If I look above Rn is satisfying this, I have a lot of them. Okay. I'm rewriting it again more clearly now. So these are the bounds. Okay. So how do we go from year to year? You just have to show. So remember, if A naught goes to infinity, expectation mk naught goes to 0. So that implies this along with this. Okay, if A naught goes to infinity, remember A naught going to infinity, I'll just, sorry for this back and forth. A naught going to infinity means expectation mk naught goes to 0. So if expectation mk naught goes to 0, I can use this. Probability, this is mk naught. Okay, remember, this is, well, in some sense, this is mk naught. for corresponding with A naught going to infinity. Okay. So I look at all the critical levels above Rn. I look at how many critical levels are there above Rn. Rn is satisfying this condition, and I get there is nothing if Rn satisfies this condition. Okay, when Rn is satisfying this condition, Rn is going off to infinity. Rn is going off to 0, but slowly, not too fast. Rn is going to 0, but slowly, because n theta d Rnd minus log n minus k minus 1 log n is going off to infinity. Okay, it is going slowly to 0. Rn will go to 0 here still. Okay, then you get this goes to 0. There is nothing, there are no critical points. And now the other end, when this is going off to infinity, that is Rn is going to 0 actually quite fast. Then what is happening is that there is always a critical point. Because here what do you prove is that variance of mk naught divided by mk naught whole square, this goes to 0. Okay, as let me write a naught goes to minus infinity. When a naught goes to minus infinity, I use the lower bound, okay, and observe that the variance divided by expectation square goes to 0. So this ratio becomes 1. Okay, that is it. So as I said, the hard work is in understanding the expectation and variance of some random quantity. Okay. So as I did last time, I do not know how many people will be there in the entire talk and so on, but I would be happy to receive some sort of a feedback on the talk, and I've created a poll on Slido. If you go to Slido, you enter this code, you can give your feedback on what did you like. Okay, just basic about the topics in the talk. That's all I've asked. If you liked any particular topic, I would be happy to know what is nice. Okay, so you can give it even at the end of the talk. I'll give a reminder. Okay, so this is the code. Okay, so I'd be happy to take it. Anything if you have. Great. Any feedback, you can just give any feedback, any open feedback, you can just enter this. I'll give the same thing at the end of the talk as well. Okay, let's get moving. I mean, somehow I find it that in an online talk, you never get to see the audience and you don't understand if people are really liking, sleeping, or watching a video. Okay, so just to understand, it would be nice. Thanks. Okay, let's recap a bit. Okay, so this is the key result. Expectation and variance both converge to the same number. Suppose I know that y is the random variable such that its expectation is equal to variance, and y is, say, integer valued. Okay, I should put here n plus to indicate union of 0. It can take 0 also. It's a very common guess in probability that often, in many cases, a natural random guess, a natural random variable satisfying this constraint is a Poisson random variable whose mean is expectation of 1. And now, what we have said is the expectation and variance of mk0 converges to dk. Conjecture, based on this, a conjecture is that mk converges weakly to y0. Okay, mk0 converges weakly to y0. This is a conjecture, just based on this, because expectation variance are converging to a same constant, and the limit, a random variable that satisfies such a constraint is a Poisson random variable. So maybe you think weakly mk0 converges to y0, where y0 is a Poisson random variable whose mean is lambda 0. Lambda 0 is nothing but this constant. Okay, this constant is what I call lambda 0. Okay, very nice. Then, what does this mean? This means convergence in distribution or weak convergence. what is convergence in distribution? Basic probability is that for every j non-negative integer, probability mk0 is equal to j converges to probability y0 equal to j. Okay, which is nothing but e to the minus lambda naught to the power j, j factorial. Okay, so if now the corollary of this, of the conjecture, if conjecture is true, if conjecture holds, if conjecture holds, then what do we get? This thing, this probability, this is equal to mk naught being greater than 1. So this is nothing but mk naught is greater than 1. So the number of critical points above level Rn being greater than 1 goes to 1 minus e to the minus lambda naught. Okay, because this is mk naught greater than or equal to 1. And mk naught, probability of mk naught greater than or equal to 1 converges to probability y naught greater than 1, which is this, and this is equal to probability. What is nice is we are able to compute the exact probability. You know, this is an exact probability. So there is this famous statement that the job of a probabilist is to compute probabilities. Okay, and often, but in very, of course, except in trivial cases, it's not possible to compute probability easily. So you look forward to approximations, you try to give approximations. Okay, so this gives you an approximation for this probability by 1 minus e to the minus lambda naught. Okay, this is approximately this. Later, I will tell you the rate of convergence. Okay, we are going to see the rate of convergence, and that is one of our contributions. Okay, let's actually, before even going to the rate of convergence, let me go something more, a higher level abstract question. Okay, what is the abstract question? Is define this new set of points, mk bar. So what am I doing? I'm taking each of the critical points ci, ri. Remember, let me mark here. mk is ci, ri. Okay, we scale all of them. Okay, I scale ci, ri. Ci is not scaled, ri is scaled in a particular fashion. Exactly the same constants as you appearing here. Okay, k minus 1 log n, this time. Now, I look at all those points in mk bar which lie, whose levels satisfy this condition. They lie in this interval, a0 to infinity. mk0 is the total number. You can see that what you can observe very trivially is that mk0 is the same as what we defined before. The number of critical points whose level is larger than this value. Okay, a0 is here. Okay, so this is some threshold. I'm looking at very large critical levels. Okay, I'm looking at very large critical levels. Okay, remember again this point. If a0 goes to infinity, there are no critical levels. So I'm looking at critical levels just before they become 0. I'm looking at the last critical levels. This is why these are called extremal critical levels. Extremal or largest. The largest critical levels is what I'm interested in. Okay, what are the largest critical levels? Okay. Now, what we showed is convergence of mk0. What ambitious goal is to show convergence of mk0 bar. What does it mean? mk0 is a random variable, is a number. mk0 bar, this is a point set. It's a set of points. I want to show convergence of set of points. Okay, not convergence of random variable. What do we mean? What do I mean by convergence of a set of points? Okay, what do I mean by this? So what do we mean by this is the following. Weak convergence, mk0, a random variable converges to another random variable. Okay, if the expectation converges for all bounded continuous functions. You take any bounded continuous function, the expectation should converge. Okay, this is what is called weak convergence in more measure theoretic language, or convergence in distribution and probability. Okay, this is equivalent. Once you have this, it is very nice. What does it mean now to talk about convergence of MK0 bar? MK0 bar converges to some zeta naught. If this is equivalent to showing, thus expectation H MK0 bar converges to expectation H zeta naught for a bounded continuous function on finite counting measures or finite point sets. Okay, I have to define a topology or metric on point sets. Forget this for the moment. I'm saying there is some nice topology on collection of point sets, collection of points. Okay, I put a nice topology. I have a continuous function. I have bounded also. I have to show this expectation converges. Okay. Okay. This is the next point at which maybe I can pause for a minute, and if anything anybody wants to ask, I can answer. Okay, this is weak convergence of, so we have made sense that showing convergence of this object of critical points and scaled critical levels is meaningful. Okay, if you have a critical level, you scale it appropriately and consider it with the critical point. This is meaningful. As I said, a job of a probabilist is to compute probabilities. In absence of probabilities, computing explicitly, we compute approximately, and to give a good approximation means you have to give the rate of convergence. Okay, so let us describe it. I will not just show that this convergence happens, I'll describe the rate of convergence from which everything follows. Okay, there is no easy way to do this, but let's get going. Give me two finite measures, I can define the total variation distance. Okay, so this is known in different ways in different things. I call it the total variation distance, or in more measure theoretic terms, sometimes people call it as the total variation of a measure, signed measure. You can think of mu minus nu as a signed measure, and this is the total variation of the signed measure. Okay, so this is what it is. Okay, this is all good. And Lipschitz, when I say a function is Lipschitz, I mean it's Lipschitz with respect to the total variation distance. That is, a function h of mu minus h of nu, if I take two finite measures, should be less than the total variation distance. I call it Lipschitz. Okay, so it's just that we are putting this as the metric. So this is, think of this as the metric. Okay, this is the metric. This is my metric on finite point sets. Okay, so this is the metric on finite point sets, and suppose you give me two random, if you give me two random point sets, okay, point process meaning point sets, then the distance between those two random ones can be measured exactly like I said before by comparing expectation on functionals, but instead I choose Lipschitz function with respect to the total variation. I look at the expectation, pick some Lipschitz function, compute the expectation, These are random variables. Okay, h of xi belongs to R, and so does h of xi prime. So these are expectation in the usual sense. Compute this, take the difference, take a supremum over all possible Lipschitz functions. This is called the Kantorowicz-Rubinstein distance. It comes from optimal transport theory. Okay, I won't describe the connection here. Okay, but what is important for us is the following, that dkr, if you Kantorowicz-Rubinstein distance goes to 0, weak convergence is true. Okay, that is, not alone is the convergence true for all Lipschitz functions, it converges for Lipschitz function, it converges uniformly, but for just bounded continuous functions, you can show you still get convergence. Okay, And even better, we get to this also. The total number of points also converges in weakly. This is convergence in distribution. This is weak convergence. Okay. So, yep. Okay. So let me, before stating our main result, let me quickly describe the what is the candidate for the limiting point process. It needs some abstraction. What is the abstraction? I want to define a Poisson point process, Poisson process on an abstract space with a underlying measure k, which is locally finite. This is the final ingredient before I can state my limit. What is it? Exactly how I describe my data. I said it's a Poisson random variable, all that. You partition your space into countable sets. Okay, each with finite measure. K of AI is finite measure. Okay, and then actually forget even this. Let me just say that all you do is on each. Okay, I would just say this: partition it into finite sets. Okay, on which K of AI is all having finite measure. On each of the sets, pick a Poisson random variable, Ni, and throw that many IID points according to the normalized distribution. Convert K into a probability distribution. Okay. If K of X is finite, then this is very simple. Okay, if K of X is finite, you are done. Very easy. If K of X is finite, then there is no problem at all, but else there is some concern here. Okay, so okay. This is a Poisson process, okay, abstract definition. And I'm not going to say some characterization and stuff. Let me get to the result itself. So come back to our setting. MK, critical points, critical levels. Remember again, these are critical points and critical levels. TD into R plus subset. And I'm doing a scaling. After the scaling, it belongs to R. Because I'm subtracting a log n and log n, I could become negative as well. And now I look at the restriction, as I said again, to just A0 to infinity. Only some critical levels, not all. I'm looking only at some critical levels. Okay. And this was the earlier result. Expectation and variance converges. What do we show? Is that we show that the entire point process, entire set of points, random points, converge to a Poisson process, which is a new it's a random point set. I will just emphasize if people miss this, it's a random point set. It is one of the most simplest random point sets. So it is very nice to know that the limit is this random point set. With this intensity measure, this is my K. I had an intensity measure. This is the density or the radon-Nikodym density of the intensity measure. Is this dk e to the minus t. This is a radon-Nikodym density. Okay. And as I said, the job is to give an approximation. Here is the approximation we are giving. Not alone do you converge to this. Okay. But you also get that the rate of convergence, good thing to note, rate of convergence goes to 0 as n goes to infinity. Okay, this is important. And let me then go tie it up to our conjecture. Maybe before. Yeah, let me just tie it up to our conjecture, this result. What is the corollary? Corollary is that cardinality of, mk bar 0, which is nothing but mk 0, converges weakly to cardinality of psi 0, and this one is a Poisson random variable with mean dk e to the minus t. Oh, sorry, dk e to the minus a naught. Okay, this is essentially the mean of the random variable, and there is a simple connection. This is also the integral from a naught to infinity, dk e to the minus t dx dt, integral over the torus as well. Okay, so this is the connection between this and this, that the total number of points, this is the conjecture we made. Okay, this was the conjecture, now it's a corollary. This is the conjecture, it holds, and what we are getting is much more stronger. Okay, this is our main, this is our result, and indeed this result itself is a corollary of a more abstract result. So let me use the last few minutes, last 10 minutes or so, to describe some overview of the abstract result. Again, let me pause for a minute. Any question, comments, or so, I'll take it.
If you're saying the critical values are described by
So, sorry, I'm unable to hear the question clearly. Hello?
Someone is asking any question?
Can you repeat the question? Your network was breaking somewhere.
No, I don't think there was any question.
Oh, okay. I heard something.
Okay, just repeat the question then. I'm audible, right?
Yeah.
Okay, so I was saying that in essence, you're saying that the critical points and the critical values are described by a Poisson point process.
In the limit.
Okay, so
And it's also nice is independent also. Somehow the intensity, if you see the intensity measure, it's a product. Okay, so that's the important thing I forgot to say.
is there any reason that we chose the Poisson point process? Like from whatever we did, it seemed like Poisson process is a natural choice. But what about something like say Brownian motion?
Okay, so firstly, it's a Poisson process because you are looking at a, let's say, a kind of a limit. Let's say Ri is being, what's happening is the expected number at this scale, like everything in, you're in probability, you have to look at the scale, it matters. Like if you have seen classical probability like strong law, Poisson, binomial convergence to Poisson, the scale matters. The scale at which we are looking at, there are very, very few critical points. And so very few critical levels. These are close to becoming zero. See, when A naught goes to infinity, this goes to zero. So I'm just looking before things vanish. So the number is a constant. So I'm getting a Poisson point process. If you want to get a Brownian motion kind of limit, what one has to do, this is a very good point, is you look at a completely different scale. Okay, you have to look at the scale where n theta d rid converges to is like a constant. You just look at the scale n theta d rid. You forget the log n and all these factors. You look at that scale, and you have to rescale things appropriately. Then you might find a Brownian motion in limit. May not be a Brownian motion, but some other Gaussian process possibly. Okay, so this log n is killing off kind of many things. It's looking at only very few things, because a lot of things are being pushed to minus infinity because of this factor being subtracted. Okay, does that answer the question to some level? Okay, maybe let me carry on. I hope it's okay.
Sorry, I was thrown out of the meeting by the bad internet connection.
Oh, okay.
I actually didn't hear you when you said that what the scenario would be in the case of a Brownian case.
Okay. Maybe can we come back to it at the end?
Yeah, sure.
Again, please remind me. Okay, sorry. Okay, let me complete things and then we can again come back. It's a good question. Thanks. Okay. So before, let me state this. Our earlier result is a consequence of another intermediate abstract result, Okay, this is not our, in fact, the main result also in the paper. This is still a corollary of our main result. What is it I want you to note is the following. Is that the distance between these two point process in Kantorowicz-Rubinstein distance is one of the stronger distances between 2-point process. Okay, so A is a subset. Remember, A is a subset of, for me, of TD cross A naught comma infinity. Okay, so A is a subset here. So it's a measure. M and L are measures. You look at the total variation distance between M and L, that is deterministic measures, and then variance minus expectation. I told you precisely when variance is equal to expectation, it's a Poisson random variable. And what does our theorem tell you? Is that if variance is converging to the expectation, variance minus expectation is converging to 0, you get a rate of convergence also. If you can quantify this, you can quantify this. And there is an easy term. Let's forget the easy term for the moment. Okay, let's forget the easy term. Okay, and now total variation distance kr. I'm just recollecting all this. So I'm not going to state our main result due to lack of time. I was always ambitious about stating it. Okay, I've kept it. I will maybe send my slides, and if people want, they can see it. Okay. So the above theorem is a consequence of our more abstract result. And once you have this, all you have to do is put the results from Bobrowski for variance and expectation, get the quantification correct, and you get the previous result. Okay. So I will just point out this point. This is essentially coming because you just quantify this convergence, you quantify here, we are done. Okay. So this is what you think. Okay. Very good. Let me not focus on the abstract result now. Let me rather give you one nice idea. How do you in general show such results? How do you obtain these kind of rates in general? Okay, this is what I'll try to do in the last 5 minutes or so. I think I have about 5 minutes. I'll do this. Okay. Where do I want to begin? I think here. Okay, not here. Okay, proof sketch. Okay. So for the proof sketch, let me do one thing. What will I do? I'll say one first point is, forget the first thing. Just think of this. The key thing is this. Let me highlight it. Take xi to be a random number. Okay, say it's a random variable. That is all. This is a beautiful idea due to Charles Stein. When Charles Stein was teaching his probability course in 1970 in Berkeley, he was not happy with the existing proofs of central limit theorem and then came up with this beautiful idea, which has revolutionized one of the most fundamental things in the last 30, 40 years in probability, I would say. Okay, it's a beautiful idea. And let me rather focus on this than our result. This is something much more useful than my result could be. Okay, even though I like my result, of course. So we want to compute this factor. Okay, remember we are defining as supremum over Lipschitz functions. Let's focus on the case of just random variables. I'm not talking about random point sets, everything, just random variables. I want to focus on this. I want to focus on expected difference of h of xi, one random variable, h of zeta, another random variable. Zeta is a Poisson random variable. Okay, that's it. I want to compute this difference for all Lipschitz function. This is what we want to do. Chen-Stein method. Louis Chen was a student of Charles Stein. Stein did it for a Gaussian random variable. Chen did it for Poisson. So it's called Chen-Stein in Poisson, Stein in general. What is the idea of Chen-Stein method or Stein method? Is you find a linear operator, or in this case a transformation, because I'm dealing with a space h is this, A, such that for any number k, we should satisfy two things. What should it satisfy? Hk minus expectation h of zeta should be A h of k. So for any k, h of k minus this expectation, this is my target, should be this. And then instead of k, if I put zeta, I should get 0 as expected. So Of course, if A satisfies this, this has to be true. But the way you actually guess it is by first finding a A that satisfies. And this should be true only for Poisson. Okay, this should be characterizing. Okay, that is also important. Okay, this is characterizing. This is a random variable, your basic probability random variable. And now, how do we compute this bound? Okay, a priori it doesn't look anything great. It just says that all you are saying is that instead of doing this, you are doing this. But I hope somebody noticed what's happened between the left-hand side and the right-hand side. There is no zeta here. That is, I wanted to compare how far is zeta from xi from zeta. I've reduced it to computing a function of xi itself. That's the beautiful thing about Stein's method, the first beautiful thing. Okay, now it's purely dependent on xi, not on zeta. Okay, you have to compute some things about xi. That's it. Okay, now first step. So let's go back to this. Stein method, I have to find an operator or a countable matrix because H is a function on natural numbers. It's an operator or a linear transformation or a countable matrix indexed by natural numbers. Okay, AH of K, satisfying this. What is my characterization? I will define the following. Let's do the following. I define an operator LH of K to be this. Okay, forget whatever the term, it's a linear, it's a nice thing. Lambda is the parameter, K is K, all that. Very quickly, this is exercise in basic probability. Even any probability student who has done a first course in probability can take it as an exercise. Okay, for all bounded functions G, this is true. For any bounded function G, a non-negative random variable or zeta, I forget to write zeta. Zeta is Poisson lambda. If and only if this is equal, true for all bounded functions. Okay, you can check that this is true only for Poisson. Now, if H is Lipschitz, you can see what's happening with Lipschitz. So I'll end in a minute. I know that I'm a couple of minutes over time, maybe. I'll end in a minute. If H is Lipschitz, G of K is bounded. Okay, H is Lipschitz means the difference is always bounded by a constant. So GK is bounded. Okay, GK is H of K minus H of K minus 1. I define this GK is bounded. And then put this GK here. What do you get? Expectation. So L H of zeta, expectation of this is 0. So this operator characterizes the Poisson random variable. So L characterizes. Okay, so this is the cool thing. L characterizes Poisson random variable. Okay, L characterizes this. Okay. Now, the last 2 minutes, I'll not say much. Just this is all we have done so far. Okay, this, how do you find a L like this? It's not magic. It's not magic. Okay, when Chen and Stein did it, it was some sort of a magic. But later people have understood how is this L arising. Okay, it arises in a very quick way. I won't say anything, but just say one thing is that L will not satisfy the first condition. L will satisfy this condition, but not the first condition. This is the problem. What is the way to go about such a L is precisely, you have to construct a Markov chain. This is for people who really know Markov chains and some advanced probability. But otherwise, you have to construct a semi-group or a Markov transition matrix, and then you look at this L PS H of K, integrate from 0 to infinity ds AH of K. This A will work. Okay, this is my A. Okay, and the reason is that there is a nice differential inequality satisfied by the semi-group. P0 is identity, exactly what you need here. P infinity is expectation H of psi. Okay, you see this two things here. The two extremes are 0 and infinity. The derivative is this. This is just integration by parts once you know these two of PS. Okay, so this is my A. And last thing I will end exactly pointing out that AH of K, essentially LPSH of K works, and then Now H is Lipschitz, LPSH is Lipschitz with the constant e to the minus s, and then everything bounds. So for any Lipschitz function, RL is the bound. RL depends only on this, okay, only zeta. Okay, so I will just stop with this. I won't say anything more, and leave with the summary. And I'll take any questions I will take. Okay. Sorry about the few minutes extra.
Thank you, Professor Yogeshwaran. So now the session is open for the questions from the audience. So if anyone has any question, please go ahead. Yeah.
If no one has any questions, then we can discuss about.
Can you speak louder? I do not know who exactly is speaking here because this from the.
I'm audible now.
Yes.
Yeah.
So if no one else has any questions, then maybe we can discuss about the Brownian case.
Okay, let's do that. Okay. Yeah. Let's go back. So, okay. What I said about the Brownian case, okay, was the following point. The way I've done my scaling, okay, the scaling is only going to be for a very large value of critical levels, and at this value, it is somehow there are very few. Okay, so it's like a discrete set of critical levels. Okay, whereas Brownian motion or a Gaussian process is something more continuous. Okay, so you need something more continuous, but my scaling is somehow making it very discrete, the critical levels. So you need to change your scaling, and what I am saying, my guess is, my intuition from what I know about this subject is that you should not have these factors at all. You just look at this. Okay, and then you should get a Gaussian process in the limit. Might not be a Brownian motion, but a Gaussian process. Okay, that is n theta RID should be like a constant. Okay, so this is something what you want to see. Okay. Yeah, and again, if you have to compute the expectation variance, I mean, first, essentially they will all go to infinity. You have to scale it suitably because A naught is going off to minus infinity. You have to scale them suitably and do a renormalization, and then you can show that it converges to Brownian motion when scaled correctly, or a Gaussian process. Okay. Yeah.
Yeah.